Welcome back. Today we're going to focus on section 12.1, the introduction to hypothesis testing. Definition 12.1 states that a statistical hypothesis is an assertion or a conjecture about the distribution of one or more random variables. If a statistical hypothesis completely specifies the distribution, it is referred to as a simple hypothesis. If not, it is referred to as a composite hypothesis. And a hypothesis test is a statistical procedure to decide if the given hypothesis is true or false. Let's consider an example from your text. This is exercise 12.2. Consider the following hypotheses and determine if each is simple or composite. The hypothesis that a random variable has a Poisson distribution with lambda equal to 1.25. In this problem, the distribution is completely specified, including a particular value for lambda. Therefore, we'll call this a simple hypothesis. If we then consider the hypothesis that a random variable has a Poisson distribution with lambda greater than 1.25, this statement no longer specifies the distribution because we're only giving a range of values for lambda instead of a particular value, so we call this a composite hypothesis. The hypothesis that a random variable has a normal distribution with mu equal to 100, well, let's remember that a normal distribution has two parameters, mu and sigma squared, and since we're not saying anything about the value of sigma squared, this must also be a composite hypothesis. Lastly, let's consider a hypothesis that a random variable has a negative binomial distribution with k equal to 3 and theta being less than 0.6. You may recall, or maybe not, either way, if you look it up, you'll see that the negative binomial distribution has two parameters, k and theta, and since we are not specifying a particular value for theta, that makes this also a composite hypothesis. Now let's talk about the components of a hypothesis test. Each hypothesis test involves the following. First, hypotheses. The null hypothesis, denoted H0, represents the current belief. The alternative or research hypothesis, denoted H1, represents the new belief. Recall that a hypothesis test is a statistical procedure employed to decide if the given hypothesis is true or false. Therefore, when we are performing any hypothesis test, we will be required to make a decision. We will either reject the null hypothesis or we will fail to reject the null hypothesis. And it's important to note that if we fail to reject the null hypothesis, we do not assume that this means that the null hypothesis will be accepted. It merely implies that there's insufficient evidence to warrant the rejection of the null hypothesis. However, generally, we want evidence to suggest that we can reject the null hypothesis in favor of the alternative hypothesis. Before we can discuss the entire framework associated with a statistical hypothesis test, what we need to do is to introduce a few more terms. In particular, the first term of interest is called the test statistic. This will be a value that we compute that measures the standardized discrepancy between the claim under the null hypothesis and the evidence observed from the sampled data. And these test statistics will be things that are somewhat familiar to us already. In particular, under certain conditions, if we're asking a question about a population mean, we might opt to compute a test statistic which just so happens to be a z-score. Meaning we might take the sample mean, subtract the hypothesized population mean, and then divide by the standard deviation over the square root of n. The other term of interest is the rejection region, which is also known as the critical region. This defines values for the test statistic for which the null hypothesis should be rejected in favor of the alternative. So we'll take our test statistic that we compute, we'll compare it to our rejection region that we'll have determined in advance, and then using that we'll make our decision. So let's consider an example where we're talking about a particular scenario, and we'll look at the different types of options that we might have for the hypotheses that we'll define. Suppose we're interested in testing a claim about the population mean body temperature of healthy adults. Possible scenarios for our hypotheses might be the following. In the first case, we might define our null hypothesis to be mu is equal to 98.6 degrees because most people would argue that the average body temperature of a healthy adult is 98.6 degrees Fahrenheit. This might be in contrast with an alternative hypothesis that mu is not equal to 98.6 degrees Fahrenheit. And we might decide this is our alternative if we're just interested in showing that the mean body temperature just differs from 98.6 degrees Fahrenheit. The second option might be to state that the mean body temperature is greater than or equal to 98.6 degrees Fahrenheit for our null hypothesis versus the alternative that the mean is strictly less than 98.6 degrees Fahrenheit. And the third option might be to state that the null hypothesis says that mu is less than or equal to 98.6 degrees Fahrenheit versus the alternative that mu is greater than 98.6 degrees Fahrenheit. Now, it's important to notice in this case that when I think about all three scenarios and I'm interested in the null hypothesis, it would have been sufficient to define the null hypothesis for all three scenarios as mu equal to 98.6 degrees Fahrenheit and not worry so much about these inequalities, the greater than or equal to or the less than or equal to 98.6. In particular, it would be enough to just say strictly equal to. And if that's the case, it really won't change the way we proceed with the problem, because in the end, our alternative hypotheses are going to deal with whether or not we're interested in something less or mean less than a number or greater than a number or just not equal to a number. It's important to notice, though, that the boundary condition for the parameter is typically included in the null hypothesis, meaning all null hypothesis statements in general are going to include the equal to portion for our parameter. So in the first case here I have mu is equal to 98.6, in the second case mu is greater than or equal to the 98.6, and in the third case mu is less than or equal to the 98.6. Now, if we revisit these sample hypotheses, in this case I want to focus solely on the alternative hypotheses. And the key point here is that when we look at these alternative hypotheses, it's going to give us a little bit more information about the kind of test that we want to perform. In particular, when we have an alternative hypothesis that states that our mean differs from a particular value, we'll call that a two-tailed test. When we have an alternative hypothesis that tells us that our mean is strictly less than a particular value, we'll call that a left-tailed test. And when we have an alternative hypothesis that states that our parameter is greater than a particular value, we'll do a right-tailed test. And this holds true for all types of hypothesis testing situations when you're saying that a parameter is either not equal to, less than, or greater than a particular value.